Good morning, everyone. My name is Yolanda Gil. I'm a director of Artificial Intelligence and Data Science Initiatives at the Viterbi School of Engineering at the University of Southern California. We want to welcome you to a USC AI Future Symposium where we showcase the research that our faculty is doing with our students and researchers on various topics of AI. Today, we are going to focus on AI on the edge. And I'm co-chairing this symposium together with Joshua Yang, who is a professor in the Department of Electrical and Computer Engineering. And he will chair this introduction section. Joshua?
Yeah, thank you, Yolanda. Hello, good morning, everyone. It's very exciting to have this symposium actually focusing on the edge AI. We know, the cloud AI, such as ChatGPT, makes the headline every day, but actually edge AI is as important, if not more important in the future. As we know, the data actually are generated at edge. We cannot really send all the data to the cloud to process, as that transfer the data will cost 10 times more energy than processing it at the edge. And the data was generated as analog, and we cannot convert all the analog data into digital and transfer and store it. So because that also costs too much time and energy. So let alone the security, and the latency issue. So that's why I think this is a very important topic, not just interesting. So I want to thank Yolanda, for actually doing most of the work, putting together this exciting symposium. And I also want to thank, the support from our dean and our school. So I will first let Yona, our dean, Yanas, to say a few words.
Thank you very much, Joshua, and thank you, Yolanda. Good morning to everyone. It's wonderful to be here today to address this opening session for AI at the edge. I'd like to say a few words about how this is developing. As you know, this is something that is has taken tremendous publicity and great progress over the last several months, actually. And it has permeated AI, obviously, but also all generative AI as well, has permeated every academic discipline and industry sector. And we must recognize the incredible innovations that we in engineering have been able to contribute here when it comes to bringing AI to all aspects of our lives in many different ways. At USC, we are very fortunate because we combine both advances in theory and on the software side, along together with advances in the hardware side. And AI in edge computing, for example, would be very important to combine both of these advances as well. So we have a great strength at the university, and it is so wonderful to see that we are offering this specific session here that combines both of them. As Joshua mentioned, edge AI will lead to better security, lower latency, less energy consumption, which is very important for sustainability questions, as well as many other benefits as well. As you know, a lot of work in this area of advancing AI has been going on at USC, particularly at ISI, that has been pioneering in large language models, machine translation, multi-agent systems, and knowledge graphs, and also on campus in many different areas as well. And those of you who have followed the recent ChatGPT saga will know that the key paper for this transformer was actually published in 2017 by one of our graduates, PhD students in CS, who did most of his work at ISI, as well as another master's student who also did work at ISI as well. And so that's something to be very proud of. I can tell you that when I posted this on LinkedIn, I felt like Kim Kardashian, because this was reposted like 60 times and it was sort of viewed by 500,000 people, which to me was like incredible. You know, whenever I post a LinkedIn post, it's probably seen, you know, maybe by 100 people or something. And so that was really extraordinary. When we go back and look at the hardware and architecture front, we have demonstrated a lot of leadership, both on campus and at ISI. At ISI, as you know, we have Moses that was pioneered in '81, and we pioneered a lot of wafer fabrication services, as well as in 2011, we had the first sort of a quantum, in quotation marks, computing computer in academia through D-Wave. I know that people argue whether D-Wave is a quantum computer or not, but for practical purposes, it acts like a quantum computer, or at least in a very non-classical way. In 2021, we formally opened the John O'Brien Nanofabrication Lab that allows us to translate novel materials to transformational devices. And I see we have here together, I can definitely see Jay Ravichandran is here, who doesn't run the Nanofabrication Lab, but he does run the CNI, which is the nanoimaging facility, which are good facilities to have in order to be able to develop the hardware that is needed for this. You will hear a lot in this symposium from our researchers, both on both sides. And I like to say a few of the words that you probably are going to hear, how we bring AI to our fingerprints from the molecular level to device and architecture level, to be able to more powerful, have more powerful sensing capabilities, potential AI implants on the body to help analyze streams of data, many other interesting and sort of far-reaching applications as well, microelectronics and optics that enable significant AI capabilities to edge devices. You will also hear on the software side the new way AI algorithms are conceived and optimized through a closer co-design. That's actually an important element there. I should mention that we're very fortunate that we recruited at USC Joshua, who joined us about a couple of years ago, and he's one of the pioneers in these areas as well. So this is actually very nicely complements the strengths that we have in many of these areas, and brings up a very unified front in attacking these particular problems. This will allow us to meet challenges of processing language with our mobile phones, discovering patterns in large relational graphs, and analyzing time series data with environmental sensors. So we're very excited to have this USC AI Future Symposium that will have a lot of thought-provoking research and innovations. Again, I'd like to thank Yolanda for being a powerful force in making this happen, not only for this particular symposium, but a number of series in this area that shows the leadership that USC has in this very, very important area as we develop, as AI becomes a very incredible, powerful technology for everything that we do. So thank you for allowing me to speak here, and I hope you have a wonderful symposium.
Thank you. Thanks a lot, Yanis. So as Yanis just mentioned, within Viterbi School, our engineering school, we have a very special institute called Information Science Institute, ISI, you probably have heard, which has played a very important role in the history of information science and also AI. So next, I'd like to have the executive director of ISI and to say a few words. Craig Knobloch.
Great, thanks, Joshua. Welcome, everyone. It's a pleasure to be here this morning, and I'm glad everyone could join us today. This general topic, AI on the edge, is a really important topic to ISI. There's, as Joshua mentioned, AI is a huge part of ISI. It's probably half of our research is in the general area of AI. And with all the recent happenings in AI, it's a very exciting time. So it's a great timing for this seminar series. So let me give you just a brief overview of sort of the topics that are the sessions that are going to be covered today. So today we're going to start out with a session on TinyML, machine learning for the edge devices, with a number of researchers, both from ISI and from other parts of Viterbi. After that, there's another second session this morning on neuromorphic computing, again, with a variety of researchers from across Viterbi, including some ISI folks. Then this morning we have an invited talk by Yiren Chen on AI to advance edge computing for next generation networks, and Yiren's from Duke University. And then we're going to close today's session with a special presentation by Steve Craigo, also an associate director here at ISI. And this is on opportunities for AI on the edge under the DoD Microelectronics Commons program. And Steve's been heavily involved in that, get proposals in that. Then tomorrow, we also have an exciting lineup of speakers. So we'll start out with a session on hardware software co-design with a variety of speakers from both ISI and Viterbi. And then the second session tomorrow morning is post-CMOS hardware and device materials with a interesting set of lineup of speakers for that. Then we're going to have a panel discussion tomorrow on AI at the frontiers of next generation computing architectures with a very distinguished series of panelists there. And then we're going to conclude tomorrow's session with some remarks from Ishwar Puri, who's our Senior Vice President for Research and Innovation. So anyway, we have an exciting lineup of speakers to both today and tomorrow, and I'm pleased that you could all join us today.
Great. Yeah, thank you, Craig. I guess we are right on time. And now let's kick off our first session. And the session chair is Jonathan May. He's a research associate professor of computer science and also a research team leader of ISI. Jonathan, the floor is yours.
Okay, thank you very much, Joshua. I'm very excited to be chairing this session, and thank you to Yolanda for inviting me, because I think I have a lot to learn here. I don't know, I know almost nothing about the hardware aspects of this, so let's learn along together. We have 4 great talks today, and let's, I think we should look at them each in turn. So why don't we move on to our first talk by Luis Garcia. Luis focuses on security and safety of learning-enabled cyber-physical systems and the Internet of Things. He's a research assistant professor at USC, and he's a research lead at ISI. He got his PhD at Rutgers, but there was another Luis Garcia who also got his PhD from Rutgers in the 80s, so please don't confuse them. I've been fortunate enough to work with Luis before. We collaborated on an exciting DARPA program to use natural language processing techniques to try to decompile binary code. So he's going to talk today about neural inertial navigation in ultra-resource constrained devices, and I don't know anything about any of that, so I'm just going to let him start. Take it away, Luis.
Thanks, John. Yeah, and I appreciate the ability to kick off these talks. So a lot of this research stemmed from my postdoc and has continued on during my early career here at USC. And a lot of what we wanted to do was, for a variety of applications, from different funding sources, we wanted to enhance situational awareness with on-device inferencing. And a lot of the applications we work with, such as search and rescue, actually a lot of it stems from underwater animal tracking or indoor UAV, indoor robots. A lot of these applications oftentimes are denied GPS and kind of traditional localization and tracking mechanisms that can. So a lot of what we looked at was seeing how leveraging inertial odometry based on the inertial measurement unit, which measures your accelerometry, and so on. And so these are just a number of applications. And if you proceed to the next slide, So this is since translated to some part of ongoing NSF work, neurocognitive systems, where we're trying to provide more context to brain signals. And part of it also requires understanding, how patients, these patients that have these implanted sensors in their brains, how fast they're moving, and as they navigate, real world environments that could go from indoors to outdoors. And in these cases, the GPS for tracking might not help as much. So we often rely on what's called dead reckoning, where you use inertial odometry based on these inertial measurement units that could be on your phone or on your wearable sensors that you have on your body that are commonplace. So if you'll proceed to the next slide. So relying on these sensors, though, can be a nuisance. Oftentimes, as you can see, when we only rely on, these are just a few runs that we had, but you can see that when we only rely on the inertial measurement unit using classical state estimation methods, oftentimes there will be a significant drift over time because we lose our essentially our fix or our reference that that you usually provided by GPS. So again, these classical model-based inertial odometries are typically not robust to domain shifts or inertial perturbations that from quick movements. So if you'll proceed to the next slide. So right now, there's in recent years been a lot of advancements in neural inertial navigation that allows us to be robust to some of these artifacts that are introduced, and they have formalized a model for predicting some of the heading rate and displacement on the azimuth plane. But again, with neural models comes computational overhead, and we want these devices, depending on what application we're using, typically to be as resource constrained as possible because they're running on batteries. And for instance, sometimes they can't be heavy devices on the underwater marine animals that we're looking at. There requires to be a very small percentage of the animal's weight. So we often have to use these very tiny devices and somehow enhance the situational awareness in real time in a robust way. So this one project, so this kind of the core of this talk is really focusing on this one project that's a kind of a microcosm for the research, where we wanted to do real-time 3D neural inertial navigation on an ultra resource constrained hardware. And this hardware is 128 kilobytes of RAM with 1 megabyte of flash, so it demands really extremely lightweight machine learning models in comparison to a smartphone that can that has 4 gigabytes of RAM and 64 gigabytes of storage. And the major contributions here was that we provided, leveraging magnetometer and physics-based models, in addition to these neural-based models, to generate these neural inertial models that are robust to inertial artifacts. And we also, in the paper, we describe how you can actually incorporate notions about the hardware in the learning pipeline. So I will briefly talk about that in a few slides. And then in addition, we add this third dimension of altitude estimation. So traditional techniques usually focus on just heading rate and estimation, but for certain applications, we want to add that third dimension where, for example, understanding how animals dive underwater, or even for drone altitude estimation and whatnot. So if you go to the next slide, or actually, yeah. So this is the architecture that is actually, in essence, neural symbolic, in the sense that we leverage a lightweight temporal convolutional neural network to read in velocity, and so it regresses velocity and to estimate displacement. But it also has the second component, which is a physics metadata module that tries to essentially leverage latent information to kind of police the outputs of the neural network model. And then this third component is based on a pressure sensor, where we try to estimate the movement in the third dimension. And so this is, in a nutshell, this paper that was, again, it was recently presented at IMWUT, and this was, ongoing work with my UCLA collaborators. And I should mention that the first author, this is, central to his thesis. So, he could probably provide many more technical details about this project. But if you'll go to the next one, so this is just giving a high-level overview of how we make this platform or hardware aware. So this uses Bayesian optimization using this an open source framework called Mango, and it allows us to essentially try to maximize the SRAM and flash usage of this platform while minimizing latency and the error of, or essentially maximizing performance of the model itself for the backbone temporal convolutional neural network. So in the paper, we describe how this optimization works and how we develop a surrogate model to enable this optimization. And then if you go to the next slide, it's just giving more details about the experimental setup, but you can see the different applications that we evaluated this particular device or these algorithms on, from pedestrian dead reckoning to underwater vehicles to UAVs, as well as animal tracking. And this is one example of the robot that they've been working on that's actually used for agriculture. So they call it the agrobot. So these are just some results. And if you go to the next slide, you can see this is a summary of the results where the model that we propose has essentially outperforms some of the state-of-the-art models while having a significant reduction in the model size that's typically used in this space. And so for my next slide, so in conclusion, so in this work, we showed that it's possible to deploy real-time and 3D neural inertial navigation on resource-constrained hardware. And it enjoys the lightweightness of these model-based techniques and the resolution of neural inertial models. And a lot of the future work that we described is really about fusing neural inertial tracking with occasional or opportunistic GPS or radio updates. So that's something that we've explored in prior works, but wasn't integrated directly into this model. And then we also making the physics metadata channel more neural symbolic. You can talk more about that offline. And then kind of the emphasizing the value of these foundational models to train task-specific models for our application. I just want to, in the next slide, I'll just conclude that we do have, if you're interested in, a higher level overview or describing a lot of the challenges and opportunities that I mentioned today, we did have a survey that I'd be happy to share. I don't think it's been published yet, but it's been accepted on these neural navigation challenges on extremely resource-constrained platforms. So thank you, everyone.
Thank you, Luis. So I see there's been at least one question, and I just wanted to make sure that we're all on the same page here. I think the way this is going to work is we're going to do these talks, and then we're going to open the floor to questions at the end. So Luis, you can answer in line, but you could also wait so that we'll have some questions to answer at the end. So I'd like to ask people, please do feel free to add your questions, and we'll get to them. We'll have a nice balance throughout. Okay, so again, thank you very much. So the next talk is by Peter Beerel, and I took down some notes in a second. So I've known Peter for a number of years, although we haven't actually formally collaborated together. He's got a PhD from Stanford and has been at USC since 1994. He's a research director at ISI. And he works in circuitry and microarchitecture and algorithms. and is in electrical and computer engineering. And I mentioned you're he's also a professor and associate chair of the computer engineering division, which you probably should have mentioned at the beginning. Yeah, with a little further ado, he's going to talk today about embedding deep learning models within tiny IoT devices.
Okay, hopefully everyone can hear me. Right, so again, my name is Peter Beerel. Thank you, Jonathan, for the introduction. I also want to thank my co-authors of this presentation, former student Shovik Kundu, now at Intel Labs, and Gaurav Data, who will be graduating soon. This is all work from their theses, and in fact, they have more. But what we'll be focusing on, if I can get this to present properly, are the challenges of getting these next generation, very good machine learning algorithms onto devices. And the basic challenges, as we keep on doing research in ML, the models are just growing and growing and growing and growing, but the hardware isn't keeping up. The hardware follows Moore's law, and actually that's tapering down. And so we can't get these wonderful algorithms on the hardware. As some people have talked about, we can go to the cloud, but that has privacy issues, that has energy issues, that has latency issues. So all we really want to be able to do as much as we can on a device. So as an example, the tiny YOLO has 7 billion multiply accumulates max, as we say it, very, very expensive. You look at the success or really the failure of something like Google Smart Glass. They're trying to do just 12 frames per second, but the battery dies within 25 minutes. And so that is not going to be an effective platform until we figure out how to simplify the models. How do we come up with a balance between accuracy in the models and the energy efficiency and latency and all that we need on device? And that's essentially what a lot of our work has been done. And I'm going to now go through a series of different works that we've done to address this challenge. Give me a second as I start my stopwatch here. Okay. Let's see if that, okay. So one of the areas that we've done is a notion of self-attentive pooling for low memory footprint. So the general idea of pooling is to downsample from a large input activation map to a smaller downsample activation map. And you would like to do this because the smaller the activation map, then the operations that you have to perform on it are all going to be fewer, and then you'll save energy. Most of the time, people do this by just looking locally within the image. We started looking at the idea of combining both local features and non-local features, kind of like what you've seen in transformers, that can provide a more aggressive downsampling and yet still good accuracy. And we've done a good number of research in here. And I have the reference at the bottom here for WACV 2023. So this is a rather recent paper. And what we're able to achieve is 4x reduction in peak memory with maybe a 1% accuracy degradation. So that's quite reasonable drop in accuracy for that much savings in peak memory for the kind of devices that Luis and others will talk about, where we just don't have the gigabytes and gigabytes of memory. And this idea is really quite effective and quite general, combining local and non-local features. So even when you consider the same memory footprint, you can actually do better in accuracy than local pooling, 1.43%, which in this domain is significant. So that's one piece of work. Let me move on to my next slide. Another thing to think about is that we can't just do model reduction in isolation. On these TinyML devices, we're going to have one model, and it better be relatively general. It may need to be able to handle things that you trained with, like a panda, plus things perhaps that you haven't trained with, or out of distribution pictures or adversarial pictures is one specific, and you have to consider both. And the problem when you consider trying a network that has been trained, that is general, it gets harder and harder to remove the weights, to prune them, which again would save energy and save power. So you have to think of this as a joint optimization problem where you're considering accuracy, generalization, as well as trying to prune the weights to make as many zero as possible. There are a variety of techniques, as sort of I try to illustrate here on the left. And Shovik has done a number of works in this area, as cited down here, some good papers. Essentially, right now, we are the state of the art in compressed models that are also robust, that are also general in his ICLR paper. But you have to really consider the optimization here and a variety of different optimization techniques that he's explored. Beyond just pruning the weights, we also want to think about reducing the number of levels of the network. If we reduce the number of levels, again, that will reduce the memory, that will reduce the latency, that will reduce the compute costs. So how can we do that? We've considered two different approaches. One is a knowledge distillation framework where we have a student-teacher framework. The teacher is maybe a very long, very detailed model. The student is one which has reduced depth. And we now need to have a hybrid, where we came up with a hybrid distillation framework that does both regular distillation as well as self-distillation, where you sort of learn from yourself to come up with a reduced network model that still has good accuracy. And we were able to show that works for actual training as well as synthetic training, which gives you some privacy advantages. So here we were able to outperform the SOTA by about 66%, particularly when training is not available. That was in Shovik's NeurIPS 2021 paper. And then more recently, we got a nice paper into ICLR 2023, which we call model linearization. And here the idea is to reduce the ReLUs, make them straight line, as much as you can. The more you can do this, the more effectively you can combine layers, because it's the ReLU nonlinearity that is separating the different layers out. And if you could do that, again, further, you can minimize latency, you can minimize cost, particularly in the private inference area, minimizing ReLU. That's where all the cost is in terms of private inference with the cryptographic protocols. So this is a wide range of applications. And we were able to show that we can get linearized, more linearized by up to a factor of 5.2x with similar and better accuracy. So this linearization will have a lot of applications, and it's kind of a new paradigm where most people worry about, again, minimizing weights or minimizing layers. Here we're minimizing the amount of nonlinearity. We've also looked a lot at these spiky neural networks. Spiky neural networks are more neurologically brain inspired, where we all know the brain is really low watts, but it doesn't work on 8-bit activations. It works on electric spikes. There is an electrical analogy where now the spikes are essentially 1 bit, and there are hardware frameworks which can optimize that, accelerators. So here, instead of doing multiplication, you're doing conditional adds. And conditional adds, when you look at the hardware, are much cheaper. And there have been some successes to get SNNs that have high accuracy very recently. For a long time, they were very, very hard to train, very hard to do anything significant, but there have been recent successes. But here the challenges are people need a lot of time steps because you're doing this over multiple time steps for every image or every sample you're looking at. And there's still a lot of spike activity that, again, affects energy. So we've been looking at that problem a lot. We have state-of-the-art methods for reducing, again, pruning and convergence using, again, distillation. And we're able to prune 33x, meaning only 3% of the weights are left. That, again, reduces spike activity. We've also worked on adversarial aspects of this, where you modify at every time step the image a little bit, and that leads to better generalization and better robustness to adversarial attacks. We've worked on a number of techniques where we optimize the thresholds of these spiky neural networks, looking and also optimizing the regularization. And doing this, again, leads to significant wins. We now, compared to ANNs, we're talking about up to 2 orders of magnitude more energy efficient if you strictly look at the compute. And we're also, again, working on the memory aspects as well. And so there's a lot of opportunities here. So I don't want to take too much more time. I again want to thank my students, Gaurav and Shovik, for helping me with all this research, driving me into new areas. It's been very fun and exciting, and we look forward to continuing this direction. Thank you.
Okay, thank you, Peter. So our next speaker is John Paul Walters. JP works out of the Arlington office, I believe. He's got his PhD from Wayne State University, and he works in many topics in heterogeneous systems, very excitingly in space systems and in edge systems, and works in fault tolerance and compilers and lots of nice heterogeneous hardware issues. And he's going to talk today about distributed transformer models in edge environments. All right.
Thank you, John. Yes, that was a great introduction to my research area. And I'm really excited that we're starting to see more and more push into these heterogeneous systems. I want to push things out into space. I want to get AI into these next generation compilers, but let's start with this edge computing stuff first. As we've heard a couple of times, can we go back a slide? As we've heard a couple of times, cloud computing has really kind of democratized access to the scalable resources that we kind of depend on in many ways, but they are really bounded by physics. You can't move bits with any lower latency than physics allows. And you don't always have a cloud to depend on, but yet we do have these surprisingly performant computers in our pockets, whether it's your cell phone or your car, whether it's a constellation in space. We can now start to utilize that onboard computation and start to push real computation out to these devices. Ultimately, what I want to do is I want to push this AI out to these edge devices to allow us to achieve these advances in things like autonomy, privacy, real-time responsiveness for like these important problems, from imaging to privacy-related work, like an in-home ChatGPT kind of system. Next slide, please. But we do have this growing challenge, and that's the parameter space. These parameters are growing at a rate that far exceeds Moore's law, and they've been doing that for a long time. And here's one reference that you'll see commonly, and Peter in the previous talk showed another. The point being, we are just rapidly scaling up the parameters in the latest state-of-the-art models, and that's adding increasing complexity to even the data center class devices that we have. One of my current soapboxes is that these large transformer models have this tendency to turn data center class GPUs into their own resource constrained devices. And this is something that we need to be thinking about, not just if you want to push something to the computational edge, but if you want to keep utilizing the latest and greatest in like AI transformers, we need a way to accommodate that. And really the problem that I'm trying to solve at the edge is just adding to this complexity, because now suddenly we have these swap constraints at size, weight, and power. We don't have a plug necessarily to plug into. We need to operate off of a battery. And we really can't continue to accommodate this like aggressive growth. And as a result, we have to think about how we're going to parallelize this computation. And just as an example, I want to point you to this figure in the lower right-hand corner. These are just a very standard set of models, BIT large, BIT huge, and the BERT, the language model. We took a few very commonly like common devices. There's a Raspberry Pi, and there's these Minnow boards. They have relatively small amount of memory, up to about 8 gigabytes for these C2558 boards. And in some cases, yeah, you can operate these models. In others, though, you're starting to experience these out of memory errors at fairly low sizes, and so you're never going to get that Raspberry Pi to operate with these massively large parameter models with a single Raspberry Pi, and that's really the problem that we're targeting. Next slide, please. So that's where we get to the work that we've been doing under ONR for the last several years, and that is the pipe edge system. Pipe Edge is really about enabling these resource-intensive transformer models on these swap-constrained devices. We want to take the model itself and we want to slice it up and distribute it across a whole bunch of these edge devices. And I'll show you some performance numbers in just the very next slide here. It allows us to suddenly actually execute these models on devices that otherwise couldn't. And then we can go a step further. By taking advantage of pipeline parallelism, we're able to actually get a performance improvement. Now, pipeline parallelism, for those of you who may not be aware, this is really analogous to kind of the classic 5-stage pipeline that you might have learned about in computer architecture. If we pipeline our models, we can achieve this level of pipeline parallelism, just as shown in that figure in the kind of upper left-hand corner. Now here we're showing kind of a 4-stage pipeline, and that's a perfectly reasonable way of looking at it. The reality is we can think about scaling this out much beyond that as well. And this has the advantage of being quite complementary to other optimization approaches. We might have, for example, layer pruning, might have quantization, and I'll talk about quantization in a bit, but it allows you to start from the original unquantized, fully accurate model, and then map that out to the devices that you're interested in. Next slide, please. So this is just one example. We've got a bunch of others in the papers that I'll point you to in just a few minutes. But it's just one example on the latest NVIDIA Orin device. And the NVIDIA Orin device is a GPU-enabled device. It's in the family of the like AGX Xavier, AGX Jetson kind of devices that you may have heard about. And these are devices that we're starting to see now in cars, in the automotive space. We're starting to see versions of the NVIDIA Jetson flown in space, some ruggedized versions. And then there are smaller power profile versions of these Jetson devices as well. In this case, I'm just looking at a couple of models, VIT large and VIT huge, and we're seeing that they're exhibiting, fairly common performance scaling characteristics. The VIT large model, we get actually quite good performance scaling out to about 3 stages. Then we start to find that the performance versus compute bottleneck starts to take over and it tapers off. Whereas the VIT huge model is much, much larger. It gives us a lot more to compute on. Here we're seeing near linear scaling out to all 5 of the devices that we're testing. And I'll also point out that the Minnow boards that I talked about in the second slide, we have results showing that those will scale out to at least 16 nodes or so. And it really gives you the power of actually targeting these performant or these computing resource intensive devices. But as I said, there's this other kind of complementary question of, how do we actually deal with these devices in the field? Because wireless networks do experience instability. This is kind of the classic instability that you'll see where compute and communication don't quite overlap. When communication takes over, then you start to experience this bottleneck. So we've also been looking at a form of quantization called post-training quantization that allows us to actually adapt the transferred bit widths in runtime. We essentially serialize or marshal up all this data, quantize it, send it out over the wire in a much more compact form, unmarshal it, and then continue our computation. That's the kind of essence of the post-training quantization, and it doesn't require us to retrain at all. Next slide, please. So this is one that we could spend quite a bit of time on, but in the interest of time, I won't do that. What I do want to point out is that this really gives us a really cool knob to target adaptivity in these kinds of systems. In the upper left-hand corner, we're looking at the stage bandwidth, and that's ultimately what we're kind of controlling as we move through these different phases, phase 0 through 4. And what I want to kind of point out is as we kind of move from phase 0 to 1, we can imagine that a knob is being turned and we're dropping bandwidth. Here we see in the stage performance, that's where we're actually looking at the images per second that we're trying to target with an output target rate. We see a brief dip And then we quantize. If you look at the figure in the upper right-hand corner, we're quantizing that down to 16-bit. We'll do that a couple of more times, ultimately in phase 2, getting down to 2-bit quantization. We're keeping the model accuracy very high. This is actually almost unchanged. Yes, we do see a bit of a drop once we get down to 2-bit quantization, and that's to be expected. But this is a real opportunity to actually perform these computations in the field when you might be able to accept a small accuracy loss as a result of the quantization. So moving forward, I think this really does give us new opportunities to move this computation to the edge. And we are really excited about looking at the limits of these of this technology, things like wildfire perimeter mapping and home automation. As I said, we've got a couple of publications. One is the Pipe Edge paper in DSD 2022, and the other will be appearing soon. So thank you.
Okay, thank you, JP. And for our final talk, I believe someone's going to present his own slides, but I'm happy to introduce Salman Avestimehr. He is a Dean's Professor, and he's first director now of the new USC Amazon Center on Secure and Trusted Machine Learning, as well as the director of the Information Theory and Machine Learning Research Lab at ECE at USC. And he got his PhD from Berkeley, and he's has a lot of awards, and he works in information theory and federated machine learning and decentralized machine learning and secure and privacy preserving learning, which I think is what he's going to mostly talk about today, based on me looking at the slides. And so his talk is called Open and Collaborative AI at the Edge. Take it away, Salman.
Hi, everybody. Thanks much. It's a pleasure to be here. Can you see my slides?
Yes. Here we go. They just went into presentation mode. Great.
Awesome. Very good. As Jonathan mentioned, here I put a little bit more focus on bringing collaboration at the edge. The idea is that not just running at one node, but running it in collaboration with many nodes who are the data owners. Maybe one way to motivate it is, as we all know, computation is heavy on the cloud, but there is a lot of valuable data at the edge. For example, a lot in the IoT domain, in the automotive domain, in the cell phones, healthcare, finance, and generally speaking, data is born at the edge. And the challenge is currently maybe the AI ecosystem, if you think about it, is driven by bringing data to the cloud, training models on the cloud, and pushing for inference at the edge. But because of the privacy regulations, maybe sensitivity of the data, huge amount of data doesn't get used and doesn't push into machine learning ecosystem. So a solution for that is gaining a lot of attention is what is called federated learning. That does the other way, brings the computation to the edge, more specifically training to the edge of the network, so you can collaboratively train across various data silos or various phones or various Alexa devices. And that way, the model is going to get smarter by learning from data without violating any privacy, security, sensitivity, etc. So how does it work? Many of you, maybe you know already FL. At a high level, it is simple. The idea of federated learning is you do local training at each device or at each silo that owns the data. And then you try to combine those locally trained models together so that you can come up with a global model. A simple way of combining is what is called averaging, but there is a lot of work on how to aggregate that. So at a high level, local training, global aggregation. Then you try to do it. You realize actually there is a ton of challenge. And this area actually last year, there were more than like 10,000 publications in this domain. So it's growing, huge amount of publications. Maybe some of the challenges that our group has been focusing on, one of them is on the algorithm design. For example, how to do the aggregation, when to do the aggregation. The other part is how to deal with data heterogeneity, personalization, fairness. Another set of broad challenges is that typically data is at the edge, but nobody is gonna label them and curate them for machine learning. So for such systems to work, we need to have mechanisms that can work with no labels, weak labels, noisy labels, and also continual set of labels that are generated. Other side of it is from scalability and system design. For example, one focus of this session is on the resource constraint edge. how would you train a large language model in a federated manner? Other side of it is these systems, the scale is going to be huge, maybe across 1 million edge devices. This is very different from a decentralized training that has been studied, maybe over 1,000 GPUs. So you have to think about from 1,000, how do I go to millions? And finally, building such a system and making it deployable is going to be very difficult, especially you have a lot of heterogeneity. You have a different set of, it's not like a controlled environment that you can choose your instances on the cloud. Here you have to deal with a lot of hardware heterogeneity. And then from algorithm to system, maybe one layer above is on the trustworthiness aspect of it. You have to make them robust, resilient, because these are open systems. You have to think about what privacies you guarantee, and potentially maybe in the future, once they get adopted widely, on the adversarial aspect. Okay, so these areas, all of those, we have a lot of publications in our group. You can take a look. Maybe the main message is this area is challenging, exciting set of problems to look at. Generally speaking, when I give a longer talks, I talk about 4 directions: how to think about privacy security aspects, how to think about the resource constraint nodes, how to do FL without labels, and another part on the scalability. For today, I thought maybe I just tell you a highlight of what you can do if you want to run it at the resource constrained edge, to have a theme with the previous speakers. All right, so let's say now you want to train a large model, maybe a large DNN transformer at the edge of the network. Then you say, cool, I'm going to use FL. Then you realize the first step of FL is to do local training at each node, and then maybe averaging those models. Then you say, oh, how am I going to fit the model on my Alexa device, right? Good luck training a large model there. So you immediately fail, and you can use FL. And something that we have been working on is to think about beyond model averaging. Like a classical FL is local training, averaging the model. And one way to generalize it is through knowledge transfer from many small models that you can run at the edge to a large model that you want to train over the cloud, right? So if you think about federated learning a little bit more broadly, then that's the way that you can formulate it as a knowledge transfer from edge to the cloud. Okay, so how can you formulate it? The challenge of it is that, it cannot be only one way, because if these small models at the edge don't become better and better, right, then the large model that you're training at the cloud will also not improve. So it's going to saturate, and the performance is not going to be good. So you need a two-way knowledge transfer for such systems to give good performance. One way we formulated this problem is our Nurip's work called federated group knowledge transfer. And the idea is that you have a two-way transfer from edge to the cloud and cloud to the edge. So you are going to have a compact CNN, which is essentially a good feature extractor that you are training at each edge node, and a large classifier at the server. Now, the idea is that these feature extractors are going to push the classifier at the edge to become better and better. And the classifier, through the backward knowledge transfer, is going to push these feature extractors to improve. You can mathematically formulate it as an alternative minimization problem. If you are interested, you can look at the paper. No time to discuss here. Essentially, you need to have a knowledge distillation loss that connects both edge and server together, and do it through alternative optimization. Now, let's see what is the promise of such approach. So let's look at a specific setting. Your goal is to train ResNet 56 across a bunch of edge nodes. Hypothetically assume that you could fit ResNet 56 on the edge nodes and use federated averaging. That's going to be the hypothetical best scenario. In FedGKT, I'm going to only put much smaller ResNet 8 at the edge nodes, and then apply FedGKT to train ResNet 56 at the server. Okay, so the comparison is ResNet 8 is 2 orders of magnitude smaller in number of parameters and the CPU usage that you are going to have for training. So the question is, with this 2 orders of magnitude less memory and compute requirement, how well do I do? Surprisingly, you do very well. Okay, so this is for training ResNet 56. This is for training ResNet 110. The first 2 rows are important. The top one is FedGKT, which is 2 orders of magnitude less compute and memory. The second row is what you would get assuming that you could fit the model. As you can see, you don't lose anything. Actually, you don't lose. Sometimes you improve. The reason you improve is that training a smaller model is becoming a more prone to generalization errors. So it slightly even helps you. And this approach is general. You can look at ResNet 56, ResNet 110. Maybe one exciting direction we have been thinking a little bit about is how to push that beyond CNNs, maybe to transformer models. Okay, so there are some works, this paper has been picked up. There are various directions that the community has been working on to improve that. All right, so I know I have 2 minutes left. Maybe I spend these 2 minutes to also talk about, let's say, beyond research. If you want to land this to practice, what can you do? And that's the company we started more than a year ago called FedML. So you can go there. This is actually a platform for launching open and collaborative AI at the edge of the network. It is like a complete MLOps ecosystem that gives you the capability of training anywhere. So that's like you can train at the mobile phones, at IoT devices, servers, then serving those models, like serve anywhere, an application ecosystem, you can bring your application, and for the collaborative part, like a Web3 platform that you let people monetize their compute and power. So this ecosystem, again, has an open source part that is, most of the, research community that are working on FL, a large amount of them are using that. For example, Google has TensorFlow federated that is ranked after us. So it's very popular in the federated learning domain. If you want to use it for research, do that. If you also want to think about real world experiments, not just simulating, we have the MLOps we provided for free for individual users you can use. There are also enterprise customers that are using that for the deployment. So let me conclude. Hopefully I convinced you. I think FL, federated learning or collaborative AI, there are a lot of exciting problems that still needs to be worked on. On the other side of it is you also want to push it to practical side. FedML is also a powerful platform. So join our open source community and we can work together. All right, thank you.
Thank you, Salman. And thank you to all of our panelists. Unfortunately, Luis had to run. There were a couple of questions that were asked in the Q&A and he answered them in text. And please, if you're interested, I encourage you to go in there. And if you have some burning questions, please do put them in the Q&A and I will relay them to the participants. We only have a few minutes because I have been taking a little bit too long to introduce people. I apologize for that. So Arvind Dasu had a couple of questions. I'm going to ask the first for Peter. He wanted to know, what's their arithmetic precision used? He says, is there room for more memory reduction if this knob could be used? And did the reduction in memory requirement cause challenges in the access patterns from DRAM, HBM, et cetera? I only kind of understand that, so I hope you can help handle that one.
Yeah, so it's a great question. We do actually use quantization quite a bit, and it can absolutely impact how you're going to manage DRAM. 8 bits is very easy. There has been research that's looked at combinations of 8 bits, 6 bits, 4 bits, even 2 bits. I think JP talked about how you can do quantization of the activations. You can do quantizations of the weights. They can be mixed. The hardware gets tricky. For GPUs, I think in 8 makes sense. For ASICs, you can be as aggressive as you want, but you have to do more design.
Okay, great. Again, I encourage people to ask questions. I'm going to ask a couple other questions before coming back to Arvind's second question for Peter. JP, I was wondering. It seems to me, I remember, we got an 8x840 machine, and it didn't work very well because we needed to turn on NVLink. And that's when it occurred to me that, it's actually the latency between the things that really starts to become the bottleneck. And I wonder in the work that you're creating, where you have what, to my naive eyes, is like a bunch of Raspberry Pis with GPUs on them that are connected. Does does latency become the big issue, and are there ways to solve that, or are we just dealing with the speed of light at this point?
Well, physics does govern things, but the ideal scenario is one where we can, as precisely as possible, overlap that communication and computations. And so that's where we really get, I think, of the advantage in quantization. If we can quantize back down to where we're roughly even with communication and computation, now we can double buffer. We can kind of mask some of that. And my intuition is that's some of what you were seeing with NVLink as well.
I see. Okay, great. And Salman, I was wondering, as a language person, I always want to ask this question. So in the work you showed, where you were, using federated techniques and then showing results on CFAR, I wonder, is this going to does this translate naturally if the signal becomes discrete? If we have, Unicode characters essentially from people's phones rather than the continuous signal of images, or are there other techniques that need to be used?
No, definitely. Actually, given that you are interested in a language model, maybe what I can do on the chat we have a library that's FedNLP. That's the one that we had a collaboration with Alexa Group. So this is dedicated for federated learning in natural language processing. So it has, a lot of the benchmarks, for example, question answering, next word prediction, tiny birds, models, etc., that you can use. There is no issue.
Okay, great. Thank you. And hopefully somebody can put that for the people at home. I see that Shangran and some of the students are on there.
Sean is the co-author of that.
Yeah, so yes. And so finally, but going back to Peter Aravin's second question, in the SNN portion of the talk, was only synchronous behavior considered, or was any form of asynchronous processing considered?
Yeah, so this is a great question. So Intel, as many of you know, has this very large neuromorphic lab where they've been pushing accelerators for spiking neural networks. This is the Loihi platform. And this is asynchronous logic, as actually I've been teaching for many years and have had a startup company and worked with those guys in the previous startup companies before they went to Intel. So asynchronous processing of spiking neural networks is still quite hot and quite relevant, but there is overhead to asynchronous. You can actually do that just not quite as well for synchronous. And the trade-off is the more sparse it is, the more sparse you have spikes going over, the better the advantage of asynchronous is.
Okay, thanks. We're over time a little bit, so I think I might hand things back to, I'm going to say Joshua or Yolanda, or just tell everybody that we got a break for about 10 minutes, and then we'll be going on with session 2, but maybe Joshua wants to say something else.
Right. Thank you, Jonathan. Yeah, this is great. And we are a little bit 5 minutes over our original, planned time. Let's get back at 10:15. Yeah, for our next session. Okay. See you in 10 minutes.